Buffer solution, many body fluids, example like blood or urine, have definite pH, and any deviation in their pH indicates malfunctioning of the body. So the control of pH is also very important in many chemical and the biochemical process. That is, there is many medical and cosmetic formulation requires that these be kept and administered at a particular pH. So the solution which resists change in the pH on dilution or with the addition of a small amount of acid or alkali is called buffer solution. The buffer solution, note the pH can be prepared from the knowing of pKa, that is acid or pKb, that is of the acid or pKb of the base, and by controlling the ratio of the salt and acid or salt and base. A mixture of acetic acid and sodium acetate act as a buffer solution around the pHs 4.75, and a mixture of ammonium chloride and ammonium hydroxide act as a buffer solution, that is the pHs 9.25. So this is called the buffer solution. Then the solubility equilibria of sparingly soluble salt. See, we already know that the solubility of ionic solid in water varies a great deal. That is, some of the these are the calcium chloride are the soluble, that they are hygroscopic nature and even absorb water vapor from atmosphere. Hygroscopic means waters, that is moisture absorbs from surroundings, that is hygroscopic. See, others have so little solubility that they are commonly termed as the insoluble. So the solubility depends on a number of factors, important amongst which are the lattice enthalpy of the salt and the solvation enthalpy of the ions in a solution. See, for a salt to dissolve in a solvent, the strong forces attraction between the ions must be overcome by the ion-solvent interaction. So the solvent enthalpy of ions is referred to in terms of the solvation, which is always negative. Solvation usually always negative. So the energy, that is the energy, is released in the process of solvation. So the amount of solvation enthalpy depend on the nature of the solvent. Suppose in case of a non-polar covalent molecule, there is solvent or solvation enthalpy is small and hence not sufficient to overcome the lattice enthalpy in the salt consequently, so that the salt does not dissolve in non-polar solvent. So in a general rule, for a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy. So that later overcome that is the overcome by former, that is each salt head has a characteristic solubility which depends on the temperatures. See, that's mean category 1, that is soluble. Solubility is greater than 0.1 molar. Category 2, like this, the slightly soluble. Slightly soluble. So this is 0.01 molar is less than solubility is less than 0.1 molar solubility. So then the category 3, sparingly soluble. So sparingly soluble, the solubility is less than 0.01 molar. Now that is consider the equilibrium between the sparingly soluble ionic salt and the saturated aqueous solution, that is the solubility product. Simply we can write like this, Sp Ksp. So this is solubility product. Here the solid like a barium sulphate in contact with the saturated aqueous solution, that is barium sulphate BaSO4 solid, the saturated solution in water. That is the equilibrium between the undissolved solid and the ion saturated solution. We can write like this: Ba2 plus aqueous and SO4 2 minus aqueous. So the equilibrium constant reaction is, the equilibrium constant for the reaction is concentration of Ba2 plus into concentration of SO4 2 minus divided by the concentration of BaSO4, barium sulphate. So here the pure solid substance, the concentration remains constant, and we can write that is Ksp is equal to K into BaSO4, that is concentration of BaSO4 is equal to concentration of Ba2 plus concentration of SO4 2 minus. So here the Ksp, the solubility product constant, or simply solubility product we can tell. So the experimental value of the Ksp in this equation at 298 Kelvin, that is 1.1 into 10 power minus 10. So this means that for solid barium sulphate in equilibrium with its saturated solution, so the product of the concentration of barium sulphate ions is equal to its solubility product constant. So the concentration of the two ions will be equal to the molar solubility of the barium sulphate. If the molar solubility is S, suppose molar solubility is S, means that is 1.1 into 10 power minus 10 is equal to S into S is equal to what? S square. So that S will become what? 1.05 into 10 power minus 5. Okay. So the molar solubility of barium sulphate is like this. So in the unit is, you have to indicate that is mole per liter. So the salt may give on dissociation two or more than two anions and cations carrying a different charges. For example, zirconium phosphate. The zirconium phosphate, here the zirconium phosphate is dissociate into 3 zirconium cations of charges plus 4, and the 4 phosphate anions charges of minus 3. So if the molar solubility of the zirconium phosphate is S, that is molar solubility is S, means then it can be seen that the stoichiometric compound of this, that is zirconium, concentration of zirconium 4 plus is equal to 3S. Okay, and the PO4, that is phosphate, PO4 3 minus is 4S. So here the Ksp, that is solubility product, is equal to 3S power 3, 4S power 4. So it will become 6912 S power 7. So or you can write it S is equal to Ksp divided by 3 power 3 into 4 power 4 into power 1 by 7. So it will become what? Ksp divided by 6912 power 1 by 7. So a solid salt of the general formula, that is Mx, that is P plus, and X Y Q minus. So with the molar solubility S, that is in equilibrium with the saturated solution, we can represent like this, that is Mx Xy solid, X Mp is like this, Mp plus aqueous, and Y X Q minus aqueous. So here the X into P plus is equal to what? That is X into P plus is equal to Y into Q minus. So and its solubility product constants are usually the Ksp is equal to concentration of, that is M P plus power X, X Q minus power Y. So it will become what? X into S power X, Y into S power Y. So here after simplifying, that is X power x power x, y power y, and s into s, x plus y. So here on rearranging, that is x into x power s power x plus y is equal to ksp divided by x power x, y power y. So solubility, that is s is equal to ksp divided by x power x, y power y, the whole power, that is 1 by x plus y. So here the KSP equation, in this equation, that is QSP. Already we seen that this QSP is the concentration of the one or more species is not in the concentration under the equilibrium. The obviously the under equilibrium condition, that is KSP is equal to QSP. That is, but otherwise it gives the direction of the process of the precipitation or dissolution. Some solubility product constants are number of common salts at 298 degree 298 Kelvin, given the table number in your textbook. The table number is 7.9 in your textbook. Look at that. Then common ion effect on solubility of the ionic solid. It is expected from Le-Chatelier's principle that if we increase the concentration of any one of the ion, it should combine with the ion of its opposite charge, and some of the salt will be the precipitated till once again, that is the KSP is equal to QSP, that reaction quotient. Similarly, the concentration of the one of the ions is decreased, more salt will dissolve in the increasing the concentration of both ions till one is again KSP is equal to QSP. So this applicable even in soluble salt like sodium chloride, except that due to higher concentration of ions, we use their activities instead of their molarities in the expressions of the QSP. Thus, if we take a saturated solution of sodium chloride and the pass HCl gas, so what happened through the pass HCl gas through it, the sodium chloride is precipitated due to increased concentration of the chloride ion available from the dissociation of the HCl. So sodium chloride, thus the obtained is a very high purity, that is sodium chloride having a very high purity, and we can get rid of impurities like sodium and magnesium sulphate like this. So the common ion effect is also used for almost complete precipitation of the particular ion as sparingly soluble salt with a very low value of the solubility products for gravimetric estimation. Thus we can precipitate silver ion as silver chloride, ferric ions and its hydroxide, and barium ion and the sulphate for the quantitative estimation. Here the solubility of weak acid like phosphate increase at lower pH. This because at lower pH of the concentration of the anion decreases due to the protonation. So this turns increase the solubility of the salt, that is KSP is equal to QSP. So we can write like this: KSP is equal to metal, that is concentration of metal plus and concentration of that halide ion. So here the equation like this: HX aqueous is dissociate, that's mean it gives H plus aqueous plus X minus aqueous. So for acid, equilibrium constant for acid is concentration of H plus aqueous into concentration of X minus aqueous divided by the concentration of HX aqueous. So here what happens that on rearranging this, you will get concentration of X divided by the concentration of HX is equal to Ka divided by the H plus, concentration of H plus. So taking inverse of both sides and adding 1, we get this Hx divided by concentration of x minus plus 1 is equal to H plus divided by concentration of H plus divided by Ka plus 1. So we get what? This Hx, concentration of Hx plus concentration of H minus divided by x minus. So you will get here also H, concentration of H plus concentration, sorry, Ka divided by Ka. So the again taking inverse, we get what happened, that is x minus concentration of x minus divided by concentration of x minus plus concentration of Hx is equal to F. This factor is equal to Ka divided by Ka plus concentration of H plus. So, so you can, the factor F, this F decreases as pH decreases. If S, the solubility of salt at a given pH, then what happens? Ksp is equal to S Fs, then is equal to what happens? S square Ka concentration of Ka divided by S square Ka divided by Ka plus into concentration of H plus. So, and what happens again? S is equal to Ksp concentration of H plus Ka divided by Ka power 1 by 2. Then the solubility S increase with concentration of H plus or decrease in pH. So this is common ion effect on the solubility of the ionic salt. Next we will discuss the numericals of equilibrium. Thank you.